Hello. In this problem, we are asked to determine the adiabatic flame temperature of methane, assuming theoretical combustion. Combustion is covered in chapter 13 in the textbook. So we'll go straight to the combustion app. We can use many different apps for this purpose, but we'll assume an open steady reactor, and that's covered under open specific branch. Steady state, and you can find combustion and chemical equilibriums here. And then we'll pick, notice that even there we have so many choices, non-premixed versus premixed combustion. So for adiabatic flame temperature, either will work, premixed or non-premixed. These left branches are for complete combustion, and on the right-hand side we have equilibrium combustion. Okay, so let's try the IG model. We'll pick non-premixed combustion. Go to the HTML5 tab to get the combustion app started. Okay, so the question is to find the flame temperature, adiabatic flame temperature of methane. So we first job is to select methane. Click the add button. So methane is our fuel. Fuel is already done. And for a standard reaction, it's very easy to pick up a standard reaction. They are categorized here. And we have a theoretical combustion with air. Theoretical combustion means we have exactly the right amount of air reacting with methane. There will be no leftover fuel or oxygen at the end of the reaction. And the reaction will be complete. That means methane and oxidizer will produce only CO2. Carbon will be fully oxidized, and H2O. So once we click the execute button, the reaction is completely balanced. You can see here there is no excess oxygen left. That's why it's called complete combustion, because C became CO2, H became H2O, and no excess oxygen. That's the definition of a theoretical combustion. So obviously our fuel, oxidizer, as well as products are all calculated and done, and notice that the atoms that is needed based on the reactants are present in the product. So the reaction is well set. Let's go to the state panel. And what do we know for fuel? State 1 is automatically locked with fuel. So we'll take atmospheric temperature and pressure. That's the incoming fuel. We'll assume they're coming at the room temperature. And oxidizer is also coming at the same temperature and pressure. We can write an equation. P2 equals P1, T2 equals T1. And of course, the mass is picked up from the reaction itself, so we cannot set it independently. To change the mass flow rate, you can go back to the reaction and change it by multiplying it by a factor if you want to. Okay, so fuel and oxidizer states are already calculated, but the products, we only know the pressure, we don't know the temperature yet, right? Pressure is the same. So we need one more condition to find the product states. Adiabatic means there is no heat transfer. So therefore, the enthalpy that flows in with fuel and oxidizer must be equal to the enthalpy that flows out with the products. We go to the I/O panel. So therefore, we can figure out the enthalpy of the product. Let's define a variable called H product, HPR, equals, okay, the enthalpy that flows in with oxygen fuel is, it will be, it's given by m dot 1 star H1 plus m dot 2 star H2 is the enthalpy that flows in with oxygen air, divided by m dot 3. So we have found the enthalpy of the products, HPR. We can use that as a variable or pick up the number, go back to the state panel, and we can write enthalpy of the product equals H PR, enthalpy of product. That's the variable name. And once we enter that, it calculates the flame temperature. T3 is calculated to be 2328 Kelvin. So that is the adiabatic flame temperature of methane. If you burn it with air, that's assuming ideal gas as the model. All the other properties are displayed here. These are the partial properties. You can click the super print button to get a complete printout of what's going on. You can see the reaction here, fuel, oxidizer products, and the properties of all states are shown here. If we use the NPG model, the perfect gas model, the adiabatic temperature you can show would be much higher because Cp is assumed a constant in the PG model.